I don't get it. Pumpkin. Cool. I don't. All right. So here we are. Welcome back, everybody. It is November 8th, and we are approaching the end of our math-focused trig review part, so we can start actually doing problems in physics with this stuff. Yesterday I asked you guys to solve this. Quick check. Yes, thumbs up. I can solve this. I'm pretty confident I got the answer right. Thumbs down says, ugh. All right. So if you have it done, which I'm not coming around to check, let's just try. We're trying to solve for A, right? Now, right now in my mind, this is how I think about it. It's negative. Don't love it. I would prefer it positive. Do you guys agree that positives are easier? So I'm going to do two things. I'm going to move this A squared over by subtracting it. I'm going to add 2bc cos A to both sides as well, just to get everything positive. Not everything, but as much of it as I can. So in doing so, let's just see what it spits out. We wind up with 2bc times the cosine of that angle A equals b squared plus c squared minus what? A squared. Cool. Nothing crazy happens yet. We're trying to solve for lowercase a, right? Now, just to check, the natural mistake, don't write this. The natural mistake that people make when they see this for the first time, somebody tries to do this. And that's not, like, I totally get it. There's one fundamental issue, though. This is 2 times b times c times the cosine of. It's not cosine times, right? This whole piece is its own number. It's an ugly number, but it's a number, which means we can't just divide by cosine. I like this, though. If we just divide by 2bc, we have only cosine of a left on the other side. I'm going to do that. So here we go. Cosine of a then looks like it should be, and it's going to be fraction land at this point, b squared plus c squared minus a squared over 2bc. Now, just like we see when, bless you, when we write the original one, you get BC showing up on the same side as BC, right? Like, that's pretty handy that it works out this way because it makes it easy to recognize the pattern. This is normally where I stop because the next little step gets ugly. How do you undo a cosine? Louder. Inverse cosine or arc cosine. Okay, I made the comment I think the other day that I'm never going to write this again, but I'm going to write it one more time. You do not have to. Algebra says, with the exception of dividing by 0 to your guys' knowledge, whatever I do to one side I can do to the other, and I'm not cheating. Okay, I undo a cosine by using the arc cosine or the inverse cosine. Now, this is a Holloway thing, but I wish it would catch on everywhere. When I write inverse trig stuff, I use a capital letter for the C or the T or the S, whatever it is. I'm going to really clearly indicate that this is what's happening. The arc cosine of this side, right? The yellow is a new operation. The arc cosine of this side. Okay, I don't normally show this. This right side will happen, but I don't normally show the left. What happens when you take an arc cosine of a cosine? They're gone, right? They undo each other. So when they undo each other, what's the only thing that remains on the left side of this equation? A. And it turns out A is exactly equal to the arc cosine of this ugly mess. Now, we don't have to write it out, but I do want to just make sure that we can see that, oh yeah, there's some pretty easy stuff. If we're solving for angle A, notice the other two sides show up first. And there's a similar language that we used when we looked at the law of cosines initially for solving for the side. We don't have to write it unless you really want it. If I wanted to find B, angle B specifically, do you think we can generalize and figure out that formula without running through all the algebra again? Let's try. Like, you can. You may not feel confident with it right now. But I know it's going to be the arc cosine of, and let's think this out. What are the two sides that aren't B? A and C, right? So here we go. The two sides that aren't B, a squared plus c squared minus, I'll take away that B now, all over 2 times what? AC, because I see that these letters just happen to show up again, and we have it. We could do the exact same thing for C. Normally, I've kind of waffled back and forth on how I approach this when we see it in trig. Don't usually solve it for the angle itself and just say I expect you guys to do it, but this is not just a pure math class, so here it is. Could you do it for C as well? Do we have to? Cool. All right. Questions, concerns, mean comments, nice compliments, anything for me? I am cool. Thank you. All right. Trig stuff. That's super fast. Oh. Yes, you guys won the contest. Y'all get donuts. How many of you guys drink coffee in here? What do you drink if not coffee? Okay, I'm not buying $1,000 worth of Red Bull for the class. Do you guys drink juice? What kind of juice? L'orange? Orange? Anybody else have a preferred pulp or no pulp?
Pulp.
You say no pulp? Oh, I love really pulpy, like chew my orange juice. But you don't like pulp? Okay, so somebody who likes pulp will still enjoy orange juice that doesn't have it. Somebody who doesn't like pulp won't enjoy orange juice. I will bring on Monday, assuming that I remember, because I don't know if you've ever met me, but I forget stuff. Assuming I remember, Monday I will have donuts and coffee and juice for you guys. I am. No, you guys won. You get the prize. Cool. Donuts, everybody's cool with just like regular old donuts. What do you call the donuts that are shaped like this? So the circular ones are the ones with jelly typically. What about the long oval ones? What do you guys call them? Long rectangular shaped donuts? That's kind of a mouthful. I call them long johns. That's what they're called where I'm from. Longs? That probably makes more sense. Yeah. Longs? Everybody cool with longs? I'll bring a couple fruit-filled ones too. Okay. I will try my very best. Some of you guys have my phone number, I think. Anybody in here have it? One person in here has it, I think. I'm debating. Do you guys have your other teachers' phone numbers? Okay, so I'm going to make you guys a deal because I've been getting later and later here in the morning. I'm going to give you guys my phone number at the end of the hour. Don't text me when you have like specific questions, but if you ever get here in the morning and the door's locked or whatever, like I don't want you to have to stand out in the cold. Don't text me. I'm really apprehensive about doing this. Don't just blindly text me. Just kidding. Just email me. That works better. Cool. I lied. All right. So one more little piece here. I'm going to keep just this one, and I'm going to move it around because everybody just hopefully worked through that with me. I'm just going to keep this one. I'm going to move it up. We have one last little piece, and then we're going to do a couple problems, and the rest of the time will be yours. So here we go. Awesome. Now, vectors have two things every time. What are the two things that vectors have? Holy whispers. Can we try that one more time, but you speak like you're humans? That wasn't any different. Okay, here we go. We look at vectors, and we spoke about it briefly the other day. A vector could start anywhere. Like, it could start at the point 2 comma pi and run to a wonky value, and that's fine and dandy. Where is it better if it starts, though? The origin. So we're going to build up a little bit of intuition just to see how this works. Your book doesn't approach this at all. I think it's silly that they don't. Let's talk about vector arithmetic. And specifically, I'm going to call this vector addition because we're not going to do any multiplication or anything right now. So, right off the bat, it would be super nice if a vector had its initial point at the origin. It would just make everything easier. So here's my question. You do not have to draw this one if you don't want to, but we're going to look at something here. Hypothetically, and I'm going to use a concrete example, then we're going to generalize it. I could have a vector that starts at 2, 1, maybe 3, 1. And this is like a pure mathy view, right? Let's say it starts at 3, 1, and it ends at 5, 5. So starts and ends is specifically stated so I know that, hey, look, there's the angle, or there's the direction it's going in, right? Initial and terminal points. That vector is not super terrible. It's not awful. But its initial point could be nicer. Where do you want the initial point to be?
Origin.
You want it to be at the origin. So if I wanted to move everything, and I don't, like, realistically it'd be infinitely many points, but I only need 2 points to draw a line, which this is a line segment. I need to move this point some distance in a particular way to get this point to move to here. Now, if that happened and this point moved to here, this vector would be easier to deal with. Do you guys agree with that? Okay, the quick question, how do we move this? How far, which direction should we move every point on this thing? 3 left and 1 down. So check this out. We're going to do that, but we're going to generalize it as we look at it. And then we'll look at this like concrete example as well. When we're looking at vector addition, the thing that I would suggest that makes this easy is the better and more clearly we can write things, the easier it's going to be. So we're going to talk about component form for a vector. Now, don't remember if we've mentioned the word component in here over the last couple days, but I think you guys have probably seen that word before. Is that true? How would you describe components of something? Part of it, like part of the whole, not like necessarily just a fraction necessarily. Do you agree that line is diagonal? And diagonal direction, like, honestly kind of sucks. But that's okay because any diagonal can be broken into 2 nicer and easier to deal with directions. There's a horizontal direction, right? So like this vector, it runs horizontally how far? From 3 to 5? 2, right? And then it goes vertically how far? 4. Is that easier than saying it goes up some square root of an ugly number? Like, that's so much nicer. When we look at a component form of a vector, all this is, and it should have been a definition, but that's fine. A way to write vectors with initial point, or where they start, they originate, at origin. Now, this would be super handy, and it's not always going to be the easiest, best thing to do. Sometimes it won't be necessary because you're just dealing with a triangle and you can work out the distances and stuff anyway. But as we look at it, when we write this, I'm going to name this vector v. You guys told me that this thing needs to move 3 left and 1 down, and every point. The initial point then would be here, right? Where would the terminal point be if this moves from 5, 5, it moves 3 left and 1 down? 2, 4. This vector is the exact same as, well, it's close because I didn't do it perfectly, but it's the same magnitude, same direction, it just has a much nicer starting point. When we're writing these, this vector v is now in what is known as component form. It's the nicest possible location. When we write this vector, we're going to say these vectors can be written vector v equals, and then this reference is getting older and older, but I call these Instagram brackets. Because if you look at people when they take pictures in neat places, peace signs are pretty common, right? Do people hold peace signs like this though anymore? Okay, right? Like it's that cheesy. Hold on. Cool. All right. So check it out. I call these my Instagram brackets. We have our initial point at the origin. Piece of cake. All I need then, if I always say we're starting at 0, 0, to describe a vector, I just need to tell you where it ends. If it starts at the origin, that's easy. Where did this one end? So this ended at 2, 4, right? So when we write these vectors, I'm just going to say it's almost like an ordered pair, x comma y, where the ordered pair xy is the terminal point. Okay, which means this vector, this orange one right here, and this is our concrete example, if I wanted to write it instead of having to talk about all these different points, which is ugly and messy and gross, I'm just going to say, check it out, vector v, the second I see my Instagram brackets, I know that we're talking about a vector that starts at the origin. And where does it end again? 4, 1. Okay, there's a bigger step out that's beyond this. If we now have this one that starts at 4, 1, could you find its distance pretty easily? Its magnitude, rather, if we use a better word. I think so. Turns out, I'm going to say and. How do we write magnitude? What's the notation we used? Hey, it's 2 vertical bars. Check it out. The magnitude of this vector v When it's in terminal form, super easy. It is the square root of x squared plus y squared. Because when we use the distance formula or Pythagorean theorem, whichever one, they're the same thing, we get that x minus 0, because that's our initial point, and that y minus 0. It's super easy to do to find this. Cool. Feeling all right with it? Okay, last little piece. I'm going to see how you guys would write the rules if you get 2. So we have nice component form. This is really convenient. It makes vector stuff really easy, or significantly easier, less messy. Last little piece. We talked about component form. I'll switch colors. Let's look at actually adding vectors. Geometrically, you can add vectors, and if you do everything exactly perfect, which nobody ever will because that really doesn't exist, you could draw them on a graph like we did the other day just to get a sense of it. How do you add vectors on a graph? Tip to tail. Cool. As we look at it, that's fine and that works, that's whatever, but if you had a way to do it without drawing them and being really precise with your drawings every time, it'd be a little easier. So here we go. Let's go ahead and say we're working with 2 vectors, and I'm going to make it look a little bit more like physics. Let's say we had one vector that's a force. We'll call it force 1. And we'll call this, I don't know, doesn't really matter as we're looking at it. Let's say it's 3, 7. So it's a diagonal force, and its total magnitude is what? That's not a nice number. 49 plus 9, root 58. So 7 point something newtons. Not a whole lot of force. Okay, they're pushing it at an angle. Now when they're pushing with that much force at an angle, 3 of the newtons of force go that direction, and 7 of them are going upward. So it's like 2 people shoving different strengths to make it a diagonal in the end. Okay, if we have this force, 3, 7, and we have force 2, let's say somebody else is pushing maybe a different direction, and this is a vector in component form, and let's say that they're fighting, and it's -4, -2. If I want to find the resultant force, which we're looking at, find, and we're just going to do a couple little pieces. On A, if I wanted to take vector 1, that force that we applied, and vector 2, this is a resultant. I'm just going to label this equals FR. I want us to find FR. We're looking for this value. Now, going through it, do we know what F1 and F2 are as vectors? So let's just plug and chug, and I'm real curious to see if you got to write the rules, and I think you're gonna get the right rule. But let's check it out. What am I gonna plug in for force 1 instead? Something. I'm gonna make a stupid duck face every time. Be prepared. Hey, love it. 3, 7 with the Instagram brackets. Here it is. 3, 7. That's force 1. Plus, do we know what force 2 is? Okay, here's my challenge for you. I'm going to give you like 30 seconds. I'm not going to tell you how this works. Just write lightly. Don't write in pen. Show me how you want this to work. What's your gut say should happen here? If you need to draw it, you can. But I want to give you guys a second just to see how it shakes out. No guidance. I want to see you add these vectors how you think it should work. Cool. Intuitively told me the same thing. I got a lot of people who got -1, 5. How on earth did you get -1, 5? You added the x parts and you added the y parts, which makes sense graphically. If we say, hey, you're going to go 3 to the right here, and then you're going to go 4 to the left. Yep, definitely we wind up at -1, and I can see it happens. Your guys' intuition there is perfect. Exactly how it needs to work is what you want it to be. -1, 5 is our resultant vector. Cool. Find me the magnitude of it. So that's an extension. Now, magnitude, or F sub r with 2 vertical bars. Find me the magnitude of that vector, and then if you're feeling super wild, go ahead and find me the angle too. We'll do an angle problem here in a minute, but you can use SOHCAHTOA or inverse SOHCAHTOA to find the angle. I'm going to give you all just a moment. I'm going to pass out some worksheets. Okay, looking at the magnitude. Super easy, super hard. What do you think? We'll see. Cool. The magnitude is equal to the square root of, what's the x value of this vector? -1. That's the x, and we're going to square it. Plus, what's the y value of this vector? 5, and we're going to square it. As an exact answer, we get root 26. 5 point, I don't know. Somebody has it. 5.10? Cool. Now, we weren't super crazy with it. If it's a force, what should it be measured in, do you think? Not old tons. So stupid. Newtons. Cool. All right. We could find the angle here. Should we find the angle here? Yeah, let's find the angle here. So we got part 1. Part 2. Let's get part 3. And this one I am going to sketch. I know the length of it. Cool. I know the not direction yet, but we're going to get there. Would sketching it help with the angle, you think? For sure. So here we go. I'm going to recognize, I know it ends at -1,5. That's all I care about. I don't care about the other parts that got to our resultant. The resultant's going to tell us everything we need. So here we go. My resultant is this guy from up to -1,5. And I'm going to write this order pair here with the understanding that you may or may not need to. Okay. I'm after the angle, and this triangle is going to be ugly. Oftentimes when we get an ugly shaped triangle just because it's so small, I might change it and distort it a little bit to make it easier to think about. In hindsight, I would like to have changed my scale, but I'm already committed. I need to find the angle that this travels at. And it turns out there's a bunch of different angles that one could get out of this deal, right? So if I'm looking at it, and you don't have to change yours, but I'm going to change mine so it looks a little bit, it's not going to be to scale anymore, but it's going to look easier to think about. All right. So here it is, and without having to pick a scale, I think I can just do this. There is a scale where this is going to be the point -1,5. And it's just a bigger triangle to look at. Okay. When I ask about the angle for which it's traveling, bunch of different answers. Somebody could give me this one, that whole angle, right? Certainly valid. If you want to use a bearing sort of angle, which is what I would suggest anytime you're talking about true direction within physics, this angle would be the one I'm after. But there's one more little wonky thing we can do. I think it's more natural for us to find this angle. And there's a lot of, 3 different choices, right? I'm just going to say angle, and I'm going to label this. 1, you don't have to label it. I just want you to talk about something. 1, 2, and 3, those are the 3 angles that you might find. Which one is the best? That's subjective, right? I'll tell you, I'm going to make a claim. I want you guys to figure out my reasoning. Angle 3 is the one that I'm going to find first. I'm going to write my answer, like angle 2, but angle 3 is the one that we're going to find initially. Why is the question. Why angle 3? I'm going to give you guys 60 seconds. I want to hear the air escaping your lungs as your vocal cords and mouth shape change the sound. Cool. 90 degrees. There's no 90-degree angle here yet. How do you make a 90-degree angle here? Oh my gosh, it's a right triangle if we drop straight down. And check it out. Do you know this side length? What is it? The vertical? 5? This one's a weird one. I'm not trying to trick you, but it's going to seem that way. What's this distance? So let's be careful. -1 isn't a distance, that's a displacement. It's a distance of 1. And I already know that this is root 26 or 5.1. Of these two numbers, if I'm doing the math and we don't have to use it, what would be the better number to put here? 5.1 or root 26? That's not correct. Why is root 26 a better choice? So there's an issue with it. Somebody has a calculator. I left. Oh, mine's my backpack. Root 26 was exactly 5.1. Is that true? Was it really? I don't think so. Yeah, anybody want to use that whole number that Fern just said? No, that sucks. But if you approximate here, you're going to throw off your answer. It's okay, though. Maybe we don't even need it. I'm going to write 5.1, but we're not going to use it. Okay, I have all this stuff. I think we can find this angle, theta. Cool. So this is actually, when we see it in pre-calc again, just so you know, this is called theta prime. Not because of your prime, totally, just so you know. This is just a new version of theta. Gosh, from this theta, and even if I say, gosh, that number is just not as nice, let's use the exact ones. And you don't have to erase yours, it's fine to be there. From this theta, what sides of this triangle, this right triangle, do I know? This side is the opposite, adjacent, or hypotenuse. Opposite. This side is the opposite, adjacent, or hypotenuse. Opposite and adjacent. Trig. Opposite and adjacent. Oh, my tangent. Tangent of theta, guaranteed, is, what's the opposite length? 5 over what's the adjacent side? Okay. How do you want to do a tangent? So arctangent, let's take the inverse. I'll do it to both sides, but again, notice this is what I was talking about earlier. I'm just going to write 5 because it's 5 over 1. I don't know what this is. Who does? What does, rather? The calculator. Ask your calculator for me, as long as it's in degrees, for the arctangent of 5. 78.7? Waiting for a second. 78.7.
Why are we using arctangent?
Because, are you cool with that this statement's true?
Yeah.
But we're trying to solve for theta, and the only way that we can undo a tangent is by using arctangent. You can't just divide it. You can't subtract. You just have to take the arctangent. And it happened to both sides, just like it did here, but I erased all the work. When I took the arc cosine of both sides to undo a cosine. Cool. Can I get a second? Cool. Now, these problems, they're going to go a lot faster. We're like hitting all the trig as we're doing it right now, and we're going to get practice. Is that really, if I just said stand up and walk at 78.7 degrees, is that the direction that they're going to go? No, because if they're a mathematician or you give them no other stuff, they're probably going to go from here, and then 78, they're going to go in this direction, which is the wrong way. Okay, so if we want to write this as a bearing, which is what I think we should do, and we will do, this is the angle that I'm really after. Cool, because I would start at north, and I would fall some amount to the west. Now, how do we find this angle, though? Hey, if this is 78.7, you add 1.3 to get to 80, you add 10 more. I think that this angle right here is 11.3 degrees. I just did 90 minus 78.7, right? Because I know that this quadrant forms a 90-degree angle in the end. So here we go. I have broken this up, and I've just kept adding a little more at a time. The resultant force. The resultant force, and I'm just going to write F sub r, has a magnitude. What was the length or the magnitude of that force? Hey, good. I just want to make sure that we could like identify it. 5.1 newtons at, gosh, what was the angle we just found? 11.3, but I can't just say 11.3. Because we get the same thing where somebody tries to walk in this direction at 11.3 degrees. To get to this angle, do we start at north or south? North, and then we're going to fall 11.3 degrees. What direction? And look at that, we have it. Cool. This is the fastest trig stuff I've ever done. My hope is that every trig piece that we've seen looks kind of familiar to you guys. You probably don't remember it perfectly, but it should be stuff that you've seen before. Have you ever seen this form of vectors, the component form? You saw it in pre-calc last year?
I don't remember what I saw.
Okay, that's fair. Awesome. Let's do a couple problems. Sweet. So I passed you guys out a worksheet, and apparently I didn't give me one, but that's okay because I have a copy of it. Running examples. So looking at this, there's like a little caveat that I want you guys to be like super aware of. I've given you all the tools that we could possibly need. Doesn't mean that every single problem is going to use all of those tools, right? Like give you a hammer and a saw, you're not going to use both simultaneously necessarily. If we look at this, the problem's kind of convoluted, but welcome to physics because they always are written in this fashion. As we look at it, I know that I am in a straight line 15 kilometers away from my camp at this angle. So right off the bat, You guys are all drawing quadrants. That's fine with me. I'm good with that. I don't think I need any south anywhere, though. I don't think so. And then beyond that, I don't have any east stuff showing. So I'm working pretty much over here. Okay. Right now, if I draw, and I'm just going to estimate, I'm going to draw the resultant that we're after. Sort of. Okay. Here I am. I'll say this is 15 kilometers right here. And I need to fall which direction? 40 degrees to the west, which is probably about here. Okay. This is my 40-degree angle. Right there. Now, here's camp. And check it out. We know it's camp because there's a beautiful tent sitting there waiting for us. Cool. Unfortunately, we can't walk straight back. So to get back, we're in the middle of the forest. The trail is going to take us which direction and how far? It's going to take me 5 kilometers north. Now, on this picture, where am I standing currently? The origin. We're sitting there and like, have you guys ever heard that as the crow flies? Did I use that language or did I get rid of it? I might be on the second one. Okay, so we're going to just start the first part of our walk. We're going to walk 5 kilometers north, and then anything else I should write on here, you think? Hey, I'm going to write 15 kilometers. So here we go. Let's start our walk back. Here we are just hanging out in the middle of the forest. We need to walk 5 kilometers north, right? So here I am. Is it going to be perfect to scale? No, but as long as stuff is labeled, it's okay. Would you believe it if I said that's 5 kilometers? Sweet. Here we go. I'm going to make that smaller. There's our first path, 5 kilometers. Now, when we look at this, the question is actually asking, once we get to this point, I need to know how far and in what direction do we need to walk. The forest is gone. I can just walk right through the field. My resultant that we're looking for starts here and ends where? At camp. That's where we're trying to get. This is the resultant vector that we're after, right here. Okay, so for that vector, I need 2 things. I need the magnitude and the direction. That's all we're after. Right off the bat, a couple questions. Is this a right triangle? It's not a right triangle. So now we need to start looking and seeing maybe we need a bigger tool. We can't just use Pythagorean theorem here. Now, luckily for us, we have an angle. As far as given information, I know several things, right? If you look in your notes, and I don't think I put it here, is there a specific situation that says, hey, law of cosines works well compared to law of sines? We talked about all the angle side, and side angle side, and side side, and all that good stuff yesterday. Help me identify, with the known information, we have one of them. And we don't normally write this, but you're probably rusty with it. We have what given to us? Angle, side, side. So here's an angle and a side and a side. Hey, I like that one more. We start at a side, then we hit an angle, and then we hit a side. I have side angle side right now. This tells me, not 100%, but pretty good suggestion that we should use what? Law of cosines. So I'm just going to say implies LOC for the law of cosines as shorthand. Now, there's no letters on this thing. And that's okay, because when we generalize stuff, the letters are irrelevant. Doesn't matter what letters we use. Are we looking for the magnitude first or the angle first? Yeah, let's find magnitude. So let's see if we can't generalize from our law of cosines to get this. The resultant's what we're after, right? Now, I think I lied to you guys the other day. The magnitude thing is nice. I'm going to keep with that in math. In here, I'm just going to use r without the mark to represent the length of it. Okay, just to make it look a little nicer. Man, law of cosines. Well, let's try. R squared. What are the lengths of the sides that aren't r? 15. So we're going to take 15, we're going to square it, plus the other side is 5 squared, minus 2 times, and then no thought needed. It's these same numbers. 15 times 5 times what? Love it. Confidently whispered cosine. And the cosine of what angle? 40 degrees. This is plug and chug. Verify on your, or try at least, on your calculator. Get me r squared equals, don't do the square root yet. Let me know, let's confirm that the right side of this equation, when you type it in, you can get the same answers. I'm sorry? This is the law of cosines.
Is this, we talked about this before?
Yep, so 2 places. It's in your notes from yesterday, but it's also on the top of the sheet.
Oh,
But this is the ugly format, but without the picture. So when we find law of cosines, we're going to find this. So the how come question, we can dig into the proof and justification if you're super interested in it. I don't have a good answer just like off the cuff.
Oh,
We have to actually dig into it.
I was looking at this one right here.
Yeah, so notice, and that's just terrible formatting error. If you look on the next line, it runs down to the next line.
Oh.
Yeah, I would scratch it out. Like, I changed it on mine immediately, but I printed it before I noticed it.
My bad. I didn't hear you say it. We'll talk about it.
What do you guys get on the right side? One more time? 76.6. Can you give me a couple more decimals? Okay. How do we get 40 degrees, Nick? You just type number 40. As long as your calculator sets to degrees. Can somebody second this? One more time. When you take the square root? You got 145 here? Okay, so let me grab my calculator because I'll also check. This is a square root? So what I have written is correct for you? Okay, so I'm just going to double check 15 squared, and my calculator guaranteed is not going to be in degrees right now. Okay, 15 squared plus 5 squared minus 2 times 5 times 15 times the cosine of 40 degrees. I get 135.09.
Yeah.
Double check yours, Fern. I'm not sure where the mistake happens. The first thing that I would think, just to check, is degrees. 135.093, right? Okay, how do I go from r squared equals that to r equals square root? And on my calculator, when I do this, I already have this big long decimal. I use caret. So right here, caret sign. And then a square root is what power? 1/2. I just raise it to the 1/2. And I get 11.62. Okay, what should the unit be here? Kilometers. Okay, cool. We have that first part. I'm going to put a star next to it. That'll be part of our answer in the end. What else do we need, though? I need the angle. So this is what I'm going to say as kind of homework. It's not a correct answer necessarily. Play around with this triangle. I want you guys to attempt, hopefully get it, by Monday. You get a couple minutes right now. Find 5 minutes another time. Try it. If you don't get the complete answer, like, I'm not super worried about it, but I want you to try it. If you're wrong, we're going to figure out why you were wrong, but I want you to try it. By Monday, find me theta. Now, just to be clear, the angle that I'm after in the end is this one right here. North, then turns some degrees west. That's what I'm after. I don't know that this is going to be the first angle that I immediately look for, but it could be. Cool. Cool. Theta by Monday.